Okay. So, section 6.2. Section 6.2 is on what we call complete graphs. Okay, so your full definition for a complete graph is a graph in which every pair of distinct vertices is joined by exactly one edge. Okay, so these are all examples of complete graphs. The first one is a graph, a complete graph of 3 vertices. So they will call this K sub 3. Okay, K means complete graph, and N is the number of vertices that are in the picture. So this middle one, they would call this K sub, what'd you say? 4. Good. K sub 4. I've got 4 vertices. And this last one would be K sub 5. Okay, so let's see if we can take a look at these pictures and answer the following questions. Number 1, if I asked you, does a complete graph have to be connected? Yeah. What would you tell me? Yes. Yes. Okay, if you take a look at all these, they are all connected. So no disconnected graph can ever be called a complete graph. Is a complete graph allowed to have loops?
Yes. No.
Do you see any loops in any of these pictures?
No.
No. We cannot have loops. Okay, so complete graph has no loops. The third question. Is a complete graph allowed to have multiple edges?
Yes. No.
No.
This is motherfucking weird. Oh, I just cut it.
Yes. This is your keyword for that one. Exactly one edge. That's why this is a no. It has to be exactly one edge.
Gosh dang it.
Okay.
Gosh darn.
Let's look at number 4. Can different vertices have a different degree? Okay, no. So let's go to this one. What's the degree of each vertex here?
2.
These are all 2s. What about this one?
3.
They're all 3s. What about this one?
4.
They're all 4s.
Oh, no.
So no, they're not allowed to have different degrees. In a complete graph, every dot has the same degree. What do you notice, though, about the degree versus how many vertices are in each one? Okay, so your amount of vertices are 1 up from your degree, or your degree is 1 less. So the degree is 1 less than vertices. Let me see if I can get the page to extend. Your degree is 1 less than your vertices. So that's going to start us off with our first. So K sub n means complete graph. Okay, this should all be at the bottom of that page. Okay. So far we know that K sub n is your complete graph. N is your number of vertices. And n minus 1 is the degree of each vertex. So this should be the little chart at the bottom of that page that we're on right now. Okay, we're going to fill in one more thing on that as soon as we're done discovering this next piece. Woo! All right. So, number of edges in a complete graph. Take a look at your graph of K sub, what are we on, 3? Okay, K sub 3. How many edges are in that graph?
3.
Go back to K sub 3. Count your edges. K sub 3. 3? Perfect. Sorry, I was looking at 4 instead of 3. My bad. Y'all are like, Miss Smith, get your life together. Okay, so we've got 3 edges. Okay, total degree of the completed graph.
2.
Total degree. So that's going to be 6. Each dot has 2, which is a total of 6. The degree of one vertex is 2, and we have 3 vertices. 2 is your degree, and we have 3 vertices. Okay, move on to K sub 4. How many edges are in K sub 4?
4.
6. Don't forget about the 2 that cross in the middle. Each degree is 3. What's my total degree?
16. Oh, wait, 12.
12. And I have 4 vertices. Yes. Huh? K sub 5. How many edges are in that crazy graph? 10.
Yeah.
Okay. Each has a degree of 4. There's 20 total degrees, and there's 5 vertices. Okay. We don't have the graph to look at for this last one. However, take a look at this. How can I calculate the total degree?
The degree of each thing times the vertices.
If I take 2 times 3, I get 6. Each has a degree of 2, and I have 3 of them. Each has a degree of 3, and I have 4 of them. Woo, I get 12. Each has a degree of 4, and I get 5 of them. There's 20. So your total degree is degree times the vertices. Degree times your vertices.
Wow.
How can you calculate the total number of edges using the total degree? How do I get from here to here? Divide by 2. Okay, so technically I can multiply the degree times the vertice and then take that answer and divide by 2, and I get the number of edges. N minus 1 is your degree, and to get your number of edges, we take n times n minus 1 divided by 2. This should look familiar. That's a formula from chapter 1 when we did pairwise comparisons. When we talked about if I have 5 players, they each need to face 4 people. So 5 would be the amount of vertices, 4 would represent your degree, and then cut that in half. This is that same exact formula. Okay, we've got one more, and then we're going to practice. Just this page. That's your homework.
Oh.
Look at her face.
All 12 by that. All 12?
Yes.
I'm not by that.
Yes.
Listen, we're going to do examples that are very close to it. Chill. Take a chill pill. Chill pill. Chillax.
I need more than that.
Okay. We're going to try to come up with how many Hamilton circuits can I find in complete graphs. So this is my graph of K sub 3, which means I have how many vertices? 3. Each has a degree of?
2.
Okay, 3 times 2 is?
6.
Divided by 2 is?
3.
That means that's how many edges you have. Okay, so somebody give me a Hamiltonian circuit that's in this graph starting at A. A, B, C, A. Which means I also have A, C, B, A, the mirror image. Is there anything else I can do in that one? No. So I have 2 Hamilton circuits. Okay? This one is K sub 4. 4 vertices, 3 degrees. 4 times 3 is 12, divided by 2, which means I have 6 edges. Okay, Hamiltonian circuit, give me one.
A, B, C, D.
A, B, C, D, A, which means I also have A, D, C, B, A. Give me another one.
A, C,
A, C, B, D, A. Okay, A, C, B, D, A, which means I also have A, D, B, C, A. Do I have any more?
Yes.
What we got?
A, D, C, B, A.
Beautiful. A, D, C, B, A, which means, oh wait, hold on. We already have that one. I lied.
Oh.
That one matches this one. There is another one. A, you said what?
We
already did that one. Instead of it being D, it could be A, D,
A, D.
B. No, we
We already got that one.
Did she just say that?
A, C.
A, C,
No, you have C.
A, C, A, D,
C, C, A.
B, C, A.
Oh.
A, D, B, C.
D, C, A.
A, B, D, C. There. A, B, D, C, A, and A, C, D, B, A. Good. So there's a total of 6 in this picture. Okay, so here is the number of distinct Hamilton circuits in all of these complete graphs. If I have a complete graph that has 3 vertices, each has a degree of 2, I have 2. If I have 4 vertices, each has a degree of 3, I have 6. 5 vertices, each has a degree of 4, I now have 24. If I up that to 6 vertices, each with a degree of 5, I now have 120. There was a formula we learned. It wasn't chapter 1, chapter 2, actually, that would give you these answers. Can anybody remember what that formula is?
You have to open that.
Give us
Good question. How do we tell
Is it the pairwise formula?
No, we already talked about the pairwise formula.
Give us some.
You tell them.
Is it
You use this symbol in English and in math.
Oh,
The exclamation point. If I factorialize 2, that means it's 2 times 1, which is 2. If I factorialize 3, that means it's 3 times 2 times 1, which is 6. Factorialize 4. 4, 3, 2, 1, 24. So if they want to know how many Hamilton circuits that are in a complete graph, it's n minus 1, because that's your degree, factorialized. That's my final one that we've got to talk about today. N minus 1 factorial is Hamilton's circuit. All right. You probably don't have any room, but if you have a scratch piece of paper, we're just going to make up some problems. We're going to just make it up. We got this. Okay.
I don't know why, but like my week has been thrown off. Like today, I for real thought was Thursday. I don't even know how.
I wish. I wish.
Like I'm just like, it's really Thursday. I do. It's Tuesday. I thought it was Thursday.
I wish it was Thursday.
You wish it was Thursday. You and me both. Sunshine.
I mean, I still work Thursday still.
I work. I don't like the weekends.
I need some actual examples so I'm not making up crap in my head that doesn't work. Oh, that's chapter 5. All right. So if I start off and tell you K sub 17, what can you tell me about K sub 17? There's 17 vertices. So if I start with K sub 17, that means I have 17 vertices. Your degree is 16.
You can do 17 minus 16 to get your thing.
You said 17 minus 16 to get your thing.
That's time.
Oh. So you're trying to find edges. So to find edges, you would take 17 times 16 and divide that by 2.
136.
Thank you. How many Hamilton circuits are here?
Do we do?
That's a big number.
How would you do it?
Do you use
Do
the
17,
What number would you start at to find Hamilton circuits?
maybe 17.
136 minus 1?
17 minus 1, which is 16.
16 factorial. It's your edges, or not your edges, your degree factorialized. Okay, which comes out to be a huge number, and no, we're not going to write that down. Okay, let's start with that's all I'm going to tell you. Your degree is 6.
So we have to have
You got to find everything else with degree of 6.
oh, my fucking God, that's not 7.
Okay, if I have a degree of 6, that means my vertices are 7.
So 13 divided by 2.
7 times 6 divided by 2.
21.
How do I find my circuits?
20 factorial. No, 6.
6 factorial, which means I have a graph that's K sub 7. Okay. I need to find one that actually is going to work that I'm not making up in my head here. Hold on. What am I looking for? Okay. So this one. Uh-oh.
Really?
This time all I gave you is you have 45 edges.
Oh.
How do I work the formula backwards if I have 45 edges?
Times that by 2.
Okay, so normally, yeah, love me. Okay. So normally I have n times n minus 1 divided by 2 equals the number of edges. Well, right now we know your edges are 45. If you're not writing this down, I suggest you do so because you are going to need this to work on that independent practice. Okay. So I believe it was Sammy that said that. First thing I need to do is get rid of this 2. Well, in order to do it, because it's being divided, I multiply both sides by 2. Okay, so that means I've got n times n minus 1, because these cancel, equals 90. Okay, well, my edges, my 2 numbers I multiply together are 1 space apart. What 2 numbers that are 1 space apart give me 90? 10 and 9. Okay, 10 times 9 gives me 90. So this is 10 and this is 9. Okay, you want the fast calculator trick on how to find the 2 numbers? Okay, so I know most of you don't have it right now, but focus for just 1 second. Okay, your calculator will give you factors. Okay, you need to remember that you need to multiply your edges by 2. Once you get 90, you can come to y equals. If you do 90 divided by x and go to your table, I can get that by multiplying 1 times 90, 2 times 45, 3 times 30, 5 times 18, 6 times 15. We don't care about the decimals. And there's 9 times 10. So you can use your calculator to find the 2 numbers that are 1 space apart that multiply together to give you that number. Okay, if it's not obvious. So we've got 9 and 10. With 9 and 10, which one of those are my vertices? 10. Which means my degree is?
9.
Which means my circuits? 9 factorial. And this is K sub 10. You want to do another one like that?
No. Yeah.
No. All right, hold on. I need to find another number of edges that's actually going to work. Let's do. Edges are now 66. What's the first thing I have to do to 66?
Do the n and the n minus 1. You will have to do n parentheses n minus 1 divided by 2 equals 66. Times that by 2 gives you a number.
So the first thing I need to do is get rid of that 2. So I multiply by 2.
And it gives you 212.
You said 132? 132. Okay, again, I can now go to my calculator and I can type into y equals 132 divided by x and go to my table. And you just keep scrolling until you find 2 numbers that are side by side. 12 and 11. Bam, there it is. So which one's my degree?
12.
So 12, which means my vertices are 11, which means my complete circuits are 11 factorial,
12.
and this is K sub 12. Guaranteed, there will be one of these on your test next week. Tuesday. Tuesday.
Wait, I have a question.
Yes. I'm sorry, Tanya. Do I need to go back?
Yes.
Let's say it is 12 and 11. How do you know what, is it the bigger number is always going to be the bigger?
Oh, I wrote that backwards. Your vertices should be on top. Your vertices will always be a bigger number.
Vertices.
Yes. because your degree is one less than your amount of vertices.
Yeah, I was looking back.
Yes.
But all the rest.
My bad, you're right. My bad. I didn't pay attention to where I put the numbers. Okay, there's one more that I need to show you how to do. Okay, this is if I give you, are we good with this page?
Yeah.
Okay, so this time, I'm not going to tell you what K sub n is. I'm not going to tell you your vertices or your degree or even your edges. All I'm going to tell you is you have 120 circuits. Okay, remember, to get your amount of circuits, I need to take your degree, which is n minus 1, and factorialize it.
That means
So that means we would start at like 8, and we would multiply by 7, by 6, by 5. We'd start at your big number and multiply down. Well, in order to do this backwards, we need to start with your small number, and instead of multiplying, we're going to divide. So watch what happens. 120 dividing by 1 does nothing. So we're going to start with 2. What do I get when I cut that in half? 60. My next number is a 3, which gives me 20. My next number is a 4. My next one would be a 5, and I get 1. Once I get 1, this is your degree. 5 factorial would give me 120. So 5 is now your degree, which means my vertices are, how do I get my edges? 6 times 5 divided by 2, 15, and this is K sub 6. Let me find another one. So we can do one more of those, and then I'm going to leave you off to work on your homework. Yes. Tomorrow. Really? That's all the sad one that they give me? Oh, no. We're going to make up something harder than that. That's easy. Let's do something harder. That's not what I wanted to do. I wanted to add a new page. Hold on. I got you. We're going to do... Okay. So, I'm not going to tell you K, I'm not going to tell you V or D or E, but I'm going to tell you your circuits are 3, 6, 2, 8, 8, 0, 0.
Oh, you what?
That's right.
Yeah.
It's not a number, so.
The answer is non
Where is one of the
factorial.
answers? Should be like 2.
That's non factorial.
It's new.
Yeah.
Hell no.
Let me run through this last one and then I'll let you go.
Yes.
Okay. So remember, we started this number and we work ourselves backwards. So we start with our small number and we divide. So we divide by 2, which gives me
18, 14, 400.
Man.
18, 14, 400. Now I divide by?
604, 80.
Now I divide by?
4. 151, 200.
Wait, 151,
Yeah,
400,
200.
1.
200.
That's too big. Or did I miss a 0 in here?
Oh, yeah, you're missing those in there.
Should that be 800?
Yeah, you're missing.
I'm missing a 0.
I only have 5.
I don't know.
All right, so now this is 151, 200. Okay. I was just looking at it weird because I was missing a 0. So now we divide that by 5. 30,240. I now divide by 6.
5,040.
I now divide by 7.
720.
I now divide by 8.
90.
I now divide by 9.
10.
I now divide by 10. 1. So this means my degree is
10 factorial.
10. Good. Circuits with 10 factorial. So if my degree is 10, my vertices are?
11.
Edges are 11 times 10 then, divided by 2.
121.
No, that's 110 divided by 2.
That's 55, yes. And that means I have K sub 11.
What is that? 11 times 11, right?
Okay. So you can do it from every aspect, no matter what I give you. Be prepared on your test to do it from any aspect. Okay. On your next page, I will come back to this in 1 second, just in case you haven't finished. On your next page, you're going to see this. This is your homework for tonight. How many edges are there at 5K sub 20? If you need to list everything out to make sure that you can do the individual pieces they need, that's fine. Okay. Everything is on here. Okay. It tells you circuits. It tells you edges, all that happy stuff. Okay. This is your homework. Okay. Any questions? Okay.